Hi everyone. Let's now continue talking about the harmonic oscillator. So again, to remind you guys, we are still talking about the harmonic oscillator. Again, we are talking about the harmonic oscillator. Yep, the harmonic oscillator. We had two sessions talking about the harmonic oscillator. Okay, so let's continue. And what I will do for today, guys, I will try to explain the harmonic oscillator with a simple way. So what I will do for that, I will use something that you know called the wave function. So I will use the wave function, and I will avoid Dirac notations. Sorry for that. So I will avoid Dirac notations, guys, for today, and I won't use them. So what I will do, I will use the wave function to describe the state. So we will use something like this, psi of x, and I will not use this, for example. To start, guys, we always when we think about the harmonic oscillator, we think about something like this: mass m and spring. So this mass is oscillating forward and backward, and let's ignore the friction for now. So there is no friction. So this mass will continue to oscillate forward and backward. So this is oscillator, and also if we have a mass connected to a string and then connected to ceiling, and this mass started to oscillate, of course it has mass m, oscillate forward and backward like this. So let's ignore the gravity for now. It can be considered as oscillator, but I will work with this kind of harmonic oscillator, and we know that the spring constant here is equal to k. This is the idea that we will use, and this is a famous problem, a simple problem. We try to treat classical mechanics problem using quantum mechanics, and this is the beauty of this topic, guys. I would like you just to enjoy the topic, and don't try to memorize anything. Enjoy the topic. We have very nice physics problem, which is the harmonic oscillator, and we try to treat this problem using quantum mechanics. So how can we do that? So the first thing, guys, that we need to know the spring force. So the force, or the spring here, has a force that can act on this mass right here, and it is equal to minus kx. This is the force that can act on the mass m. This is the spring force. Now, guys, if we have the force, we can also so this is from classical mechanics. I will indicate that. So this is from classical. So this is from classical mechanics. I will use another thing, guys, from classical mechanics. So what is that? I will use something called the potential energy. The potential energy in classical mechanics, guys, which is V or U, you can use any kind of letters you would like. It is equal to minus W. What is W here? W here is the work done. So this is the work done using this force that you can see right here. So that's great. We know this equation. So what does that mean? That means, guys, if we try to figure out the potential energy, we need to write V is equal to minus W, and that's equal to the integration actually from 0 to x, because the object is going from the equilibrium point, which is 0, to x, and then return back to the equilibrium point, and then go to minus x, and etc. So this is what we will use, guys. And I will use here fx and dx to integrate with respect to x. And that's equal to, so that's equal to integration from 0 to x, and we have here like minus kx dx. This is the integration that can help us to figure out the potential energy of the potential energy that can be stored in this spring or in this oscillator right here. Now we know that the integration here is easy, and we often just write the answer without any extra work, because this kind of integration is super duper easy, tedious. So now we can write that V is equal to, we have here minus k x squared divided by 2. This is how can we figure out the potential energy. But I made here a big mistake. So we know that we have minus sign here, this minus sign should be here, that means we have positive here, and we have positive here. Yes, so that means the potential is equal to 1/2 kx squared. So this is the potential energy, guys, for the harmonic oscillator. So now when you look at to this potential, you can see that it is function of x, and if you try to draw this potential, you will notice that it is kind of parabola. So this is v and this is x, so it should be like this. So this is x squared. Yeah, so this is the potential of the harmonic oscillator, and the harmonic oscillator will oscillate inside this potential. So that's great. We know that, but we can add another thing, guys, about the mass. So the mass of the oscillator actually will oscillate with angular frequency omega, and I can write that down here for you. So what we have, so just the mass of this oscillator will oscillate with the frequency omega, and we don't need to prove that, just have it like this. So this is the frequency, guys. This is the frequency of the mass. So the mass of the oscillator will oscillate with this frequency, which is equal to square root k over m. This is the spring constant, and this is the mass of the object, and we can try to extract here something that is k is equal to m omega squared. So k, the spring constant, is equal to m omega squared. So that's great. That's great. We know something here very important. Everything here, guys, actually has something to do with the classical mechanics. We still didn't study we still didn't use the quantum mechanics. So this is page number 1. So have it here and continue working here on page number 2. So this is page number 2. Now, guys, since we know the potential Now we can write Schrödinger equation. Before you do anything, you need to remember Schrödinger equation. So what is Schrödinger equation? Schrödinger equation for this kind of problem, guys, can be written like this. We studied that, and as I mentioned, guys, so what I will do, I will use wave function instead of Dirac notations, because the wave function is easier and can help you to understand what I'm talking about. I know last session you were confused about the harmonic oscillator, but I think after this session I think you will feel good. So we have minus h bar squared over 2m, and we have partial squared psi as a function of x over partial x squared, and here we have the potential v of x times psi of x, and that's equal to e times psi of x. So this is Schrödinger equation in general, and since we have psi just function of x, so we can write Schrödinger equation as you can see right here. So we have minus h bar squared over 2m, and we can have complete derivative d squared psi of x over dx squared. So this is a very important thing that you need to keep in mind, because psi is just function of x. So that's why, guys, what we need to do here, we just need to have the complete derivative, as you can see right here, and then plus v as a function of x, psi of x, and that's equal to e times psi of x. So this is Schrödinger equation now. Great. But we can add here something. So what is that? I will add the potential, which is 1/2 m omega squared x squared. So I will add that here to Schrödinger equation. Once I do that, Schrödinger equation will be written as you can see. So we will have h power squared over 2m, and we have d squared psi as a function of x over dx squared, and here we have plus 1/2 m omega squared x squared times psi as a function of x, and that's equal to e as a function of x as well. Great, nice equation right here that can help us to guys, to try to understand or to try to solve the harmonic oscillator problem using quantum mechanics. So that's great, and there is very important thing that we need to keep in mind, guys, that we need to work on this equation and have everything just in one side. How can we do that? So I will write this equation like this, so minus h bar squared over 2m, and we have d squared psi as a function of x over dx squared plus here we still have 1/2 m omega squared x squared psi of x and minus e times psi of x. So that's equal to 0. So we have everything moved to the left hand side. Now we need to do another thing, guys. We need to multiply the whole equation by -1, and also multiply the whole equation by 2m over h bar squared. We need to get rid of this part right here. So when we do that, so we'll have d squared psi of x over dx squared. So here we have minus sign. We have 2m over h power squared times this. So that will give me, guys, m omega over h power squared. And here we have x squared psi of x. So this is one thing. Minus e times 2m over h power squared. So that's equal to 2me over h power squared times psi of x. So that's equal to 0. Now Schrödinger equation became a little bit nicer. So it looks like differential equation now. So it is a differential equation right here, but I just organize it. So you have it nice and clear. But we still need to do another thing, guys, that we need to have those two. We know that they are in common with psi of x, so we can do the following. So we can do d squared psi of x over dx squared. And let's see here, I think I made a mistake here. So negative sign, this should be positive. So this should be positive. So now we can do that. So positive, we have 2me over h power squared, and minus, we have m omega over h power squared x squared times psi of x, that's equal to 0. And now we have very nice equation. So this is Schrödinger equation, but it was organized, so that can make it easy to figure out solution for this differential equation. But I will mention to one thing here. I will avoid using solving the differential equation, because that will be a little bit complicated. So what I will do, I will just suggest solution with constants, and those constants can be figured out, that's fine, with some conditions. So we don't need to solve a differential equation. I will show you how can we do that. So I will start by giving a name to this part right here and another name for this part right here. So I will name 2me over h power squared. So I will name that beta, and I will name m omega over h power, so I will name that alpha. And then we can write Schrödinger equation as you can see here. So we have d squared psi of x over dx squared plus, open the parentheses, we have here beta minus alpha squared x, close the parentheses, we have psi of x, and that's equal to 0. So this is the simplest way, guys, to solve the harmonic oscillator. And by the way, here I'm solving this problem just in one dimension along x-axis. So we have this oscillator right here oscillating along x-axis. So it is oscillating, guys, along x-axis. So it is, so this problem in one dimension. It can be in 2 dimensions, it can be in 3 dimensions, so that's totally fine. But for simplicity, I prefer to have it just in 1 dimension. So once we do that, guys, so we have this differential equation, we will try to have a solution for this differential equation. And what is the best idea to do that? It is to suggest a solution. So the solution that I will suggest, guys, is that psi as a function of x is equal to a constant a. We don't know what is this constant. We will figure out this constant, but for now let's keep it a times exponential minus c x squared. So this can be a good function, good solution. And what I will do now, guys, I will try to apply this solution on Schrödinger equation and make it equal to 0 and figure out those two constants based on this condition. So we need to have c and a in order this equation is equal to 0. This is what I will do. This is another simple way, guys, to figure out the wave function for Schrödinger equation. So what I will do right now, so I will simply differentiate this with respect to x. So what I will have d psi of x over dx. So that's equal to minus 2 c a x exponential minus cx squared, and that's equal to minus 2 c x times psi of x. So this is one thing. Now we need to differentiate this equation again. So what do we have? We have d psi of x over dx2, and that's equal to, so what do we have? We have minus 2 ca exponential minus cx squared. So yeah, that's great. And then plus we have here, yeah, we will have here 4 c squared x squared times a exponential minus c x squared. So that's equal to minus 2 c times psi of x plus 4 c squared x squared times psi of x. So this is what will happen when we differentiate this equation twice. Now what we need to do, guys, we need to substitute d squared psi over dx squared with what we have here, and substitute psi of x with what we have right here, and then make everything is equal to 0. So I will write Schrödinger equation now with this way. So we'll have here minus 2. So this is d squared psi over dx squared. So I have minus 2 c psi of x plus 4 c squared x squared psi of x plus I have beta minus alpha squared x times psi of x, x squared here and x squared here as well, I'm sorry, yeah. X squared here and x squared here. So that's equal to 0. I think it is a good idea to have like different colors. I will bring different color for you guys. I was hoping to use the marker, but there is no way to use the marker. So I will try to figure out if there is. Yes. Here is another color here, so we can use a different color. So psi of x will be cancelled with psi of x, will be cancelled with psi of x, and we will end up with this equation. So we have minus 2c plus 4c squared x squared plus beta minus alpha squared x squared is equal to 0, or beta minus alpha squared x squared is equal to 2c minus 4c squared x squared. We know, guys, that beta is equal to 2c and alpha squared is equal to 4c squared. If the whole equation here is equal to 0, so we need to have this condition. So this is equal to this, and this is equal to this. So that is that's great, I think. So now we can do the following, guys, from this relation number 1, and this is relation number 2. So from relation number 1, guys, we can see that c is equal to beta over 2, and from this relation number 2, what we can see that c is equal to alpha over 2. So two different values for c, but they are equal. So here you can see that beta is equal to alpha. So how is that? I will try to show you that here. So beta is equal to alpha, so we need to have beta is equal to alpha. We know that beta is equal to 2me over h power squared, and we know that alpha is equal to m omega divided by h power. So that will give me E is equal to 1/2. Let's see here. Yeah. So is equal E is equal to 1/2 h power omega. So yeah. So this is the energy, guys. This is actually the energy of the ground state. We will see that. We will see that. So this is actually the energy. This is the energy, guys. Yeah, so this is actually the energy of the ground state. We will see that. And when we try to apply that here, guys, we will notice that C is equal to see that if we have, so it should be, guys, h power it should be omega m over 2h power. Yes, so let me try to substitute that. So for example, here alpha is equal to m omega over h power, but we have 2 here, so c is equal to m omega over 2h power. So this is the ground state that we will study, but not right now. We will go back now to the equation and substitute c that we have right here. This c that we have right here, we will substitute, guys, this c with m omega over 2h power. So that is great. So this is one part. So this is page number 3. So I have it here, and okay, so now let's move to page number 4 and continue working. So if we go to the differential equation that we can, if we go to the wave function, which is a exponential minus cx squared, let's write that down. Psi of x is equal to a exponential minus c x squared, so that's great. Now we can substitute c with m omega over 2h power. Now the wave function will be psi of x is equal to a exponential minus m omega over 2 h bar times x squared. So this is now the wave function. So this is the wave function, guys, and that's great. And we mentioned that the ground state of one-dimensional harmonic oscillator, I will write that down here. So the ground state of one-dimensional harmonic oscillator actually is equal to 1/2 h bar omega. So this is the ground state. So here in the harmonic oscillator, it is something impossible to have the ground state is equal to 0. So that's impossible. It is impossible to have the ground state of the harmonic oscillator is equal to 0. There are some problems that can have 0 ground state but not the harmonic oscillator. So the ground state of the harmonic oscillator is not 0. So now, guys, if we try to imagine the energy levels, of the harmonic oscillator, so we can see that they are equally spaced. What do I mean by equally spaced? So there is equal spaces between the energy levels, guys. I can draw that for you, and this energy space actually is equal to h bar omega. So this is the energy space, guys, and I will try to show you that. If we try to draw the energy for the harmonic oscillator, it should be like this. So we have x-axis here, we have the energy here, and try to create some lines here, or dashed lines. These dashed lines represent the energy levels. I will use now different color. So here, guys, we should have ground state. So this is E0. This is the second state. So this is E1. Here we have E2, and here we have E3. Now, guys, since this space, for example, is h bar omega, and this space is h bar omega, and this space is h bar omega, you need to continue adding h bar omega for each one of them. So here we will have, for example, like 1/2 h bar omega. This is the ground state energy, and then we will have h bar omega plus 1/2 h bar omega, so that will give me 3/2 h bar omega, and then another h bar omega, so that will give me 5/2 h bar omega, and then, guys, here we will have 7/2 h bar omega. That means, so what does that mean? I will show you that. So what does that mean, guys? So you can see here the ground state. This is the ground state. This is the first excited state. This is the second excited state, and this is the third excited state. And you can see that the space between those energy levels are equal. So here we can conclude that En, so N here can be 10, 11, 12, any energy level. So En is equal to N plus 1/2 h bar omega. So this can give you, guys, the energy for any energy level for the harmonic oscillator. Now, what you can see, guys, here, you can see that this way, or using for example, or if we use, for example, the wave function, you will see that using the wave function, guys, can be like easy way to solve the harmonic oscillator problem. We will go through Dirac notations again, but I prefer to show you that, since some of you last time were confused and asked me if we are studying the harmonic oscillator or we are studying something different. So my answer for you guys is that we are studying the harmonic oscillator, and I explained that for the third time for you using the wave function. So now we use the wave function to study the harmonic oscillator. Again, if you are confused about what we are talking, so this is the harmonic oscillator, guys. Spring, mass, surface or frictionless surface. If we oscillated or moved this mass maybe to the right and then release it, we will notice that the mass will oscillate. Right, left, right, left, right, left. So this is what we are talking about. We know that this problem is from classical mechanics, and what we are doing now, we are using quantum mechanics to solve this problem. Hopefully that's clear, guys. So now we will move to some important part when we study the harmonic oscillator. So one of these important things, guys, is the following. We need to study something called the probability. So the probability, guys, for the harmonic oscillator can be represented as the following. So actually, if we have psi of x multiplied by psi of x star, so this is called probability. So this is the probability, guys. And if we try to draw it, for example, for the ground state, if we draw it for the ground state, so what will happen? It can be, guys, drawn like this. So this is for the ground. This is for the ground state. So it can be like this. This is the probability for the ground state, and for the second excited state, it can be drawn like this. So we can draw it like this. So it can be drawn like this. So you can see, guys, that the particle or the oscillator in the ground state can be in this potential right here, and also, guys, in the second excited state, so we can see that the oscillator can be inside this potential, as you can see, but this is the probability. If we go outside the potential or the harmonic oscillator potential, so we can see that the probability will go down. So the probability here is higher and then go down if we go out of this border, for example, or this potential. Now let's have another example, which is, guys, the second excited state. So it can be drawn like this, but you can see, guys, that that we will have something like this. So this point right here is higher than this point. So this is what happens to the harmonic oscillator. So we have, this is the potential. So this is the probability of finding the oscillator inside the harmonic oscillator potential. And maybe, guys, I can jump to so this is ground state. I will write that down. This is the ground state. This is the first excited state. This is the third. This is fourth. So maybe I can jump to the fifth, or or higher. Or higher. I mean, if we jump to another higher, like higher energy level, so we will notice that we have something like this, exactly like this, guys. So this, I will try to draw that for you. So 1 2 3 4, 1 2 3, 1 2 3 4. Yeah, something like this. And you can see here, guys, what will happen to the probability inside the harmonic oscillator. So outside, the probability will go down, as you can see, to disappear, and we will have zero probability after some time. But here inside we still have probability, so it can decrease and decrease, and something like this. So this can describe the probability, the probability of finding the oscillator inside this potential, for example. And the probability actually is psi of x times psi of x star. This is the complex conjugate, guys. So that's great. What we will try to do now, we will try to adjust this a little bit, like this. Okay, yes, that's great. So what I will try to do now, guys, I will try to do some activities based on solving this problem, which is solving the harmonic oscillator problem. One of these activities, guys, is figuring out the normalization constant of this equation. So let's figure out the normalization constant. How can we do that? So that's great. So this is page number 5. I have